Hi, and welcome back to another LeetCode problem. This time we're going to look at the medium one, 1091, shortest path in a binary matrix. And yeah, we're going to do our usual. We're going to look at the problem description, the constraints, the examples, come up with an idea of how we could solve it, and do an implementation and a runtime analysis, space complexity analysis, all hopefully without any mistakes, and hopefully we will be able to communicate exactly what we're doing while we're doing it, which is great interview practice. So let's go. All right, so we're given an n by n binary matrix in form of a grid, and we should return the length of the shortest path in the matrix. If there's no clear path, return -1. Okay, shortest clear path to where? The clear path in the binary matrix is a path from the top left cell at position 0, 0 to the bottom right cell. Okay, such that all visited cells of the path are 0 and all the adjacent cells of the path are 8 directional connected. So 8 directional means we can go diagonal and we can go up, down, left, right, and then of course in the 4 diagonal directions. Okay, the length of the clear path is the number of visited cells on this path. Okay, and we should find the shortest clear path if it exists. Constraint, so we have a length of the grid, and here we can see that the grid is actually square, right? And okay, so the size of the grid is also bounded. It's at least one cell, but at most we have 100 times 100 cells. And each cell only has the value 0 or 1. Okay, cool. Now for our runtime analysis, we're going to ignore the fact that n is bounded. Otherwise, everything will be constant space and constant time, as we already know. So yeah, so let's have a look at the examples. Example 1. So what is the shortest path from here to here? Well, it's one diagonal step, right? And the length of the path is the number of cells that we visited. So it's not just one step, it's 2 cells, 0 and 0. So that's the output. Let's look at the next example. Here, the only clear path, well, the shortest clear path is to go from this 0 to that, do a diagonal step, and go down here. It also go all the way to the top right corner and then go down, but that's not the shortest path. So yeah, so that's what we then have to do, and we visit 1, 2, 3, 4 cells. Another grid example is this grid. Here, the top left cell is already 1, so there is no path, which is why we return -1. Okay, cool. So I'm thinking we are going to, well, since we're going from the top left to the top bottom, we can probably do a dynamic programming approach, but one that is very simple. So we could compute for every cell in the first row how many steps it takes to get there from the top left corner, if we can get there. And then we iterate through the next row and we see what are the values of the cells above. Do they have a minimum value? Oh, which of the above cells is a 0? Or diagonally above is a 0? And then we pick the one that has the minimum path from all those predecessors. And that should work if there is a path. Yeah, that should work. I'm just thinking, could it be possible that maybe we run into an issue where if we do this approach, we could get stuck? That could be the case, right? Because if you always go from left to right, maybe maybe there are no predecessors here. So maybe it's a better strategy. Yeah, I think it's a better strategy if we start from one cell and then we just do a breadth first search. And whenever we reach the bottom left, that's the shortest path. And if we can't reach it, then we just return 0. Yeah, so if we do a breadth first search, that means the time and space complexity is going to be n squared. Well, actually, I think the space complexity would be n, not n squared, if I'm not mistaken. But yeah, let's try to implement that solution first, and then we'll see if maybe we come up with something more difficult. And O of n space, I believe, and we have to check that in the end. You know, when we do breadth first search, we have a frontier from which we are well, we have a number of cells that form the front of our search. So if we imagine that all the cells in the grid are 0, and we start in the top left, and each step we're adding the next possible number of zeros, at the end, the maximum number of cells that are in our current queue in our breadth first search is actually 2n minus 1. So that's the worst case when all of the cells are 0. So that's dependent on n, right? It's not n squared, it's n. And we must also prevent visiting previous cells. So that could very well be O of n squared. So yeah, so we probably have to also have n squared space. So yeah. So that's my preliminary analysis of space and time. And yeah, let's now implement this. Well, for breadth first search, what I like to do, I like to use a deck, FIFO, and in Python, you can import it like this. From collections, import deck. And we're just going to initialize it like this. And the first thing that we're going to put into that thing is, of course, our starting position. So I'm going to append that position, x0, y0, and we're going to also get, of course, the size of the grid. We're going to need that as well. And yeah, and then we'll just enter our little while loop. So implementing breadth first search should become second nature to you. It's always the same thing. So you keep iterating while you have elements in your queue. And then for each element in your queue, well, yeah, you pop all the elements from the queue and process them. And while you do that, you push the next elements into the same queue. And a nice trick to do that is just to use a for loop for, and we don't actually care what the counter is, in range length of queue. This length will be evaluated once. So even if here we pop elements out of the queue, it won't change for how long the for loop runs. So this will run for exactly how many elements are in the queue before we've entered basically the for loop. So then we pop the element out, and we now need to compute the neighbors of this element. So I would say, let's see, for parse in get neighbors of that position, we're going to add that to the queue if we can. Now, that is, by the way, also a common trick that you can use in an interview. You know, you can just say, okay, let's say we have a get neighbors function. I'm going to implement that in a moment. So you don't have to implement that right away of a position, and this one should return all the neighbors. This helps you keep your code clean and you know, deal with some of the details later. And we also need to have well, a hash set that tells us which cells we've already visited so that we don't go in circles. And we just going to, well, we call it visited. And that's going to be a set. I don't know if there's a good way to order that visually, but I think that should be good enough. Yeah, like that. So, and one more thing we need to do is at the beginning, we need to check if our position is actually a valid one, right? We saw this example where the initial cell was already 1 and we can't go there. So that means we actually have to check if, you know, the grid at that position is 1 or not. So if it's 1, we'll just ignore this and continue. And so x and y is basically the position X and Y is the position that we get out. The first index is Y because that takes the row of the grid. So that's essentially the Y, and X is then the column. So that's how you do that. That's also common, and you should know that when you have a two-dimensional grid, the first index is always the Y position and the second one is always the X position. Cool. So yeah. So we're going to get the neighbors, and actually we can also, well, we can get them, and then we just check if pause in visited. We're just going to continue. We're just going to ignore it. We're not going to do anything. If you haven't visited the position yet, then we're just going to add it to our queue. That's what we'll do. And one more thing, we have to add this position, of course, to our visited. All right, so visited, add position. Yeah. I'll just do it like this. Cool. Now, well, we might be putting cells with value 1 in there. We don't want to do that, so let's do it here. Next, what else do we do? Well, when we pop out a position, we have to check if it's the destination, right? If x equals n minus 1 and y equals n minus 1, then we're done. And the minimum path length, we also have to keep track of that. And we will do so by first initializing it with 0. And every time we enter our while loop, our for loop, that means we're taking one step further, right? So that's what we're doing here. So every time we just increase, every time we're in here, we are increasing our path length. And if we never find the final position, then we're going to return -1 because we couldn't reach the end. So yes, I think the code is a little bit messy right now. Maybe we can clean that up a little bit better. Yeah, we could maybe just say, put the position like so to clean up that. And we could say if pos equals goal, then we're going to return the path length. And in the beginning, we're going to define our goal. That is nothing but n minus 1, n minus 1. We could do that. We could also simply say if its pos is equal to this, and then we save another variable. And you see here, we're going to use, tuples for the positions so that we can use them inside our little hash set as keys. I don't think you can use arrays as keys. So that's what we have to do. So here, we actually have to insert the tuple 0, 0 for the starting position. And just because we have so many variables, I'm just going to rename result to, I'm just going to rename the path length to result. There you go. And yes, so let's just go through this real quick. So we increase the number of steps by 1 every time we process our queue. When we pop an element out of the queue, we first check if it's actually a valid cell that we can enter. And if we can't, we just continue. So even if we're at the goal position, we can't enter if it's a 1 and not a 0 there. So that means we check if we've reached a goal position after we've checked if it's a valid position. And if it is, we return the current length of the path, which will be the minimal one since we're using breadth first search. Cool. So now we need to implement the getNeighbors method. The getNeighbors, we have an X and a Y that is in the position. And yeah, we need to now, let's say if this is our position x and y equals 1, we need to now return all of these neighbors, all of them. And there's also a reoccurring theme in LeetCode problems that you should probably know, and it's how to compute all of the neighbors of a cell giving a xy coordinates. And it goes like this. So what I usually use for dx dy in zip. So we're going to iterate over all of the deltas that exist here. You can do that. Or if you want to, you can iterate with for dx in -1, 1, 1. It's basically the same things. You can write that as 2 loops or with zip in 1 loop. Dy in -1, 0, 1. And then we just make a simple check if dx is 0 and dy equals 0, right? That means we're actually at the original position. Then we're going to ignore that. And otherwise, we're going to append the position to our neighbor's array. So we will do this append, and then we append the position. And again, we're using tuples. And that is basically x plus delta x and y plus delta y. So yeah, that's how you can do that. Or you do that dx dy in zip dx dy. But now you need to add more values so that you get all combinations of x and y. This is very useful when you only want to compute the top, left, right, and bottom neighbors. But if you want to compute all diagonal neighbors, I think 2 loops is the better solution. So yeah, so that's our getNeighbors function. We have the length of the grid. Now another thing, oh yeah, I'm moving on too fast. So another thing to do is to actually check, if this position is actually a valid position. Might be an invalid one, right? So px, we're going to use intermediate py equals x plus dx and y plus dy. Px, py, and then we just do the check. If px smaller 0 or px larger or equal n, we're going to continue because that means we're out of bounds, out of the grid. So that cell is not a neighbor. Same for the y position. Py, py, yeah. That is pretty much that. And doesn't really make a difference in which order we do that. Maybe that's visually more appealing, I don't know. Yes, so we're appending it to our neighbor's array, and then we iterate over all of the positions. We could call it next position if we wanted to make it a little bit more clearer, to distinguish it from position. Yeah, and we could, yeah, that's pretty much it. I think we're good to go. I'm just gonna hit the run button to see any major errors maybe in the syntax. Yes, and it's already doing this. So px, py, px, there's a typo there. Okay, so that seems to work. And well, that increased my confidence that it actually works. So I'm just going to run the code through all of the test cases. Let's see what happens. Interesting. That's taking a long time. That probably means that there is a better solution that is faster that we should have a look at. That is interesting. So the problem is, I suspect that for LeetCode, we're adding too many elements to our deck. So what we could do, we could find a solution where we have one space where we reuse the grid as to store the path lengths, right? So, and the way we could do that is, so we'll get rid of our visited set, and we will still have, I suppose, n squared time complexity, but reduce the space complexity. We are going to get rid of the visited hash set. And instead what we're going to do is we're going to write the path length as a negative number in the cell where we were at. So result is, that is our path length, right? So if we pop an element out, and if the element is a 1, we're going to ignore it. If it is 0, let me just think about this. Yes, so if we encounter a cell with a 0 at any point in time, that means that this is the shortest path to that particular 0. That is what that means. So I don't think we have to change our logic a lot here. So, okay, so what we will do, if we visit a cell, we're going to write into that cell the value of, like I said, so we're going to write into the grid at that position, we're going to write minus a result. So that's the distance to that cell, right? And when we compute the neighbors, maybe we should also check. I see what we'll do here. What we do is if the value in the cell is not 0, we're going to continue, because that means we visited that cell before. It either has a value of 1, in which case we can't visit it, or it has a value of some negative number, which means we have already visited it, so we don't have to go there again. So that's what we should do. And here, when we compute our neighbors, we should probably do the same check, right? So if the position at px, py, so that'll be py, px, is not 0, we're not interested, right? I'm going to move that value up here again as well. And so we're making sure that we only add neighbors where we know that they have not been visited before. So this is our has been visited check. And so we append them. But because doing the processing of all the elements in the queue, at the time when we process them, we might have a neighbor of an element that is also in the queue where the value is still 0. So that neighbor element that is in the current queue might get added to the next queue as well. That is why, we still have to perform this check here. Yes. All right, I'm happy with that. Let's try to run this. I should really check if I have any syntax errors first. In an interview, I would definitely do this, but now I kind of don't want to spend too much time on it, to be honest. So that works. So let's give it another try to see if our solution is now fast enough to be judged by the LeetCode. Yeah, and it is. So there you go. I don't think the solution we had before was wrong because it passed the test, but it couldn't pass like the big tests that where we get larger grids and where the runtime actually matters, like the actual runtime on the CPU, not the asymptotic one. Yeah, so I think that concludes that problem. Went from quadratic space to constant space. We're using the grid. I would recommend that you implement both solutions and try to talk through it, maybe similar to how I did it. That gives you practice for the interview. and helps anybody who sees you coding to understand what your thought process is. And it's okay if you make mistakes, if your thought process is not perfect. It's much better to be explaining what you're doing than to be quiet trying to find the perfect solution. Yeah, and it takes practice to talk and code at the same time. I feel like I do make more mistakes when I speak while coding, but yeah, I'm also currently practicing to get better at that. Thanks for watching.